The moon has fascinated humanity for millennia, serving as both a guiding light in the night sky and a focal point for scientific inquiry. One of the most fundamental aspects of the moon's relationship to Earth is its size. While it is much smaller than Earth, the moon plays a crucial role in our planet's natural rhythms, influencing tides, stabilizing Earth's axial tilt, and even impacting the length of days. Understanding the moon's size compared to Earth allows us to appreciate the dynamics between the two celestial bodies and the fundamental forces that govern their interactions. The moon's diameter is approximately 3,474 kilometers, which is about 27% of Earth's diameter, which measures around 12,142 kilometers. This means that the moon's diameter is roughly a quarter of the Earth's. To visualize this difference, imagine Earth as a basketball with a diameter of around 12 centimeters. In comparison, the moon would be the size of a tennis ball with a diameter of just over 3 centimeters. The circumference of the moon is roughly 10,121 kilometers, which is just over a quarter of Earth's circumference, which is about 40,075 kilometers. These measurements make it clear that, while the moon is much smaller than Earth, it is still large enough to have a significant impact on Earth, especially in terms of gravity and the tides. The volume of the moon is about 21.9 million cubic kilometers, which is approximately 2% of Earth's volume of 1 million cubic kilometers. This means that Earth's volume is roughly 49 times larger than the moon's volume. The moon's surface area is approximately 38 million square kilometers, which is roughly 7.4% of Earth's surface area of about 510 million square kilometers. This difference in surface area can be attributed to the vast contrast in the sizes of the two bodies, which has profound implications for the surface features and the ability of both celestial bodies to support life and interact with their surroundings. The Earth's surface, which is largely covered by oceans, mountains, forests, and deserts, is much more diverse and complex in its geological features than the moon's barren, cratered expanse. The moon's mass is about 7.35 x 10^22 kilograms, which is roughly 181 of Earth's mass. Despite the vast difference in mass, the moon's relatively small size does not prevent it from exerting considerable gravitational force on Earth. The mass of the moon is directly related to its ability to influence Earth, particularly in terms of tides and the length of days. The moon's average density is about 3.34 grams per cubic centimeter, which is lower than Earth's average density of 5.52 grams per cubic centimeter. This indicates that the moon is made of less dense material than Earth, with a composition that suggests a higher proportion of lighter elements, such as oxygen, silicon, magnesium, and iron, which make up the moon's crust. The Earth, in comparison, has a more differentiated interior, with a dense iron-nickel core and a varied mantle that contributes to its higher density. The moon's lower density is thought to result from its origin, particularly the hypothesis that it formed from the debris of a collision between Earth and a Mars-sized body, known as Theia, around 4.5 billion years ago. The resulting material from this impact was rich in silicate minerals, which contributed to the moon's comparatively lower density. In contrast, Earth's internal differentiation due to its larger mass and gravitational pull resulted in a denser composition overall. The size of the moon, particularly its mass, plays a crucial role in the gravitational relationship it shares with Earth. The moon's gravity is only about 1/6 of Earth's gravity, meaning that a person weighing 60 kilograms on Earth would weigh just 10 kilograms on the moon. This difference in gravity is due to the moon's lower mass and smaller size. Despite this, the moon's gravity is still strong enough to create significant effects on Earth. One of the most noticeable impacts of the moon's gravity on Earth is the creation of tides. The gravitational pull of the moon causes the Earth's oceans to bulge outward on the side of the planet facing the moon, creating a high tide. On the opposite side of Earth, another high tide occurs due to the centrifugal force caused by the Earth-Moon system's rotation. These tidal forces are not only crucial for oceanic processes, but also play a role in stabilizing Earth's climate and rotation. The Moon's gravitational pull also has a stabilizing effect on Earth's axial tilt. Without the Moon, Earth's axial tilt would vary much more dramatically over time, which could result in extreme climate fluctuations. The Moon's gravitational influence helps to keep Earth's axial tilt relatively stable, which is important for maintaining the planet's climate over long periods. The Moon's size and mass also have a direct impact on the length of Earth's day. The gravitational interaction between Earth and the Moon leads to tidal friction, which gradually slows Earth's rotation. This phenomenon causes the length of Earth's day to increase over time. Currently, Earth's day is about 24 hours, but billions of years ago, Earth's day was much shorter, possibly as short as 6 hours. As the Moon continues to exert its tidal forces, it will gradually cause Earth's day to lengthen, although this process happens at an extremely slow rate. Additionally, as Earth's rotation slows, the Moon is gradually moving away from Earth, at a rate of about 3.8 centimeters per year. The size and gravitational influence of the Moon also affect Earth's orbit. The Moon is the primary factor in Earth's slightly elliptical orbit, although this effect is relatively minor compared to the more dominant influence of the Sun. The Moon's gravitational pull causes Earth to wobble slightly as it orbits the Sun, a phenomenon known as lunar precession. This wobble can affect Earth's climate and has been linked to long-term cycles in the planet's climate patterns, such as ice ages. Although the Moon's size and mass are not large enough to significantly alter Earth's orbit, they still play an important role in maintaining the stability of our planet's position in the solar system. The Moon's size and the forces it exerts on Earth have contributed significantly to the development of life on our planet. The tidal forces created by the Moon have not only shaped the Earth's oceans, but also influenced the evolution of life in the tidal zones. The regular ebb and flow of the tides likely provided the necessary environmental conditions for early life forms to evolve. Furthermore, the stability in Earth's axial tilt, thanks to the Moon's gravitational pull, has played a key role in maintaining relatively stable climatic conditions, which have allowed complex life to thrive over geological timescales. The presence of the Moon also offers some unique benefits to life on Earth. For instance, the Moon's reflective surface provides a source of light in the night sky, which has likely influenced animal behaviors and contributed to the development of nocturnal species. The consistent cycle of the lunar phases, which influences the length of days and the timing of seasons, also plays a role in the life cycles of various species. In summary, the size of the Moon compared to Earth is strikingly small, yet its influence on our planet is profound. With a diameter only a quarter of Earth's, a mass just 1/81 of Earth's, and a density lower than that of Earth, the Moon is much smaller than Earth in almost every measurable way. Despite its smaller size, the Moon's gravitational pull has a significant impact on Earth, affecting everything from tides and climate stability to the length of days and the orbit of our planet. The Moon's smaller size relative to Earth, combined with its unique composition and position in the Earth-Moon system, makes it one of the most fascinating objects in our solar system. Through the study of the Moon's size and its interactions with Earth, scientists can gain valuable insights into the dynamics of planetary systems, the evolution of celestial bodies, and the complex relationships that shape life on Earth.